Vamos a empezar nuestra primera conferencia sobre minería de datos a escala poblacional para análisis social y económico. Y pues estamos muy contentos de tener a Joshua Blumenstock con nosotros para hablar. Esta es la tercera vez que lo invitamos para venir al colegio y estoy muy contento y muy agradecido que por fin hayamos podido coincidir y que hayas podido venir para este evento. Entonces, muchas gracias, Josh. Entonces, para las preguntas y respuestas, dado el número que somos, ¿no se escucha bien? ¿Sí? Dado el número que somos, van a pasar papelitos. Entonces, hacen las preguntas en los papelitos y voy a tratar de organizarlas de la mejor manera posible para hacer las preguntas a Josh. Las pueden escribir en inglés o en español, no hay ningún problema. Bueno, sin más preámbulo, déjenme presentar a Josh. Josh Blumenstock is assistant professor at the UC Berkeley School of Information and the director of the Data Intensive Development Lab. His research lies at the intersection of machine learning and development economics and focuses on using novel data and methods to better understand the causes and consequences of global poverty. At Berkeley, Joshua teaches courses in machine learning and data-intensive development. Previously, Joshua was on the faculty at the University of Washington, where he led the school's Data for Social Good initiative. He has a PhD in information science and a MA in economics from UC Berkeley, and bachelor's degrees in computer science and physics from Wesleyan University. He's a recipient of multiple grants and has different publications, including in the journal Science. And we're very happy to have you here, Josh. The floor is yours. Thank you.
Working? Yeah? ¿Sí? Okay. Por favor, discúlpenme por hablar en inglés. Creo que es lo mejor para todos si no intenté hacerlo en español. So, first of all, thank you to Raimundo, to Inegi, to Colegio de México for inviting me here. I'm very happy and flattered to be the keynote speaker. And so what I'm going to talk about today is a broader research initiative in this area at the intersection of big data and machine learning and development. And so the work that I do and my lab does really focuses on several key areas, but for the sake of today, since it's only about a half an hour that I'll be speaking, I'm going to focus on this one area here, which is using novel data and novel methods to improve measurement, and in particular the measurement of poverty and broader measures of welfare. So just to motivate briefly, when you look at traditional quantitative data coming from a lot of developing countries, the data that you get, and by you I mean a social scientist, researcher, or a policymaker, or a humanitarian organization, or even a private company who's working in a developing country, the data can be very out of date and unreliable. And so I apologize if the slides are a little bit small, but what this table is showing you is how many years it's been in a non-representative, but a sample of developing countries since they had a full national census. And you can see that in many countries it's been several decades. And to give you a sense of what that means in terms of how out of date the numbers can be, what I'm showing down here is, so Angola did their most recent census in 2014, and prior to that, the most recent census was in 1970, so 44 years apart. And if you look at how much the population changed between those two successive censuses, there's like 400% population growth. Not to mention the fact that there was a devastating civil war, there was mass internal and international migration, demographic shifts, and demographic transitions. And so put yourselves in the shoes of not just a social scientist like Ray, but a policymaker like some of the people in this room, and if the most up-to-date data you have looks like this, it just really constrains your ability to design effective policy. And so there was a nice quote by the late Secretary General for the United Nations, Kofi Annan. He wrote an opinion piece in the journal Nature, and so the quote is up here, and I'll just read what he said. So he notes that data gaps undermine our ability to target resources, to develop policies, and to track accountability. Without good data, we're flying blind. If you can't see it, you can't solve it. And what I like is he closes with this point that better data brings an imperative to design better policy. In a sense, if you don't know who the poorest people in the population are, it's easy to justify not giving them resources and giving the resources instead to your nephew or to your ethnic party in a favorite district. But if this is very well documented with open, transparent data, it creates a layer of accountability that I think is desirable. And so how have people measured, like, what are the traditional ways that people have gone about measuring poverty and welfare? If you look at the social science literature, and in particular the economics literature, there's a very heavy reliance on household face-to-face surveys. So the two most ubiquitous, or the most common large-scale nationally representative surveys are the demographic and health surveys and the living standard and measurement surveys. And each of these surveys is done in a large number of countries with some regular frequency. And just as a side note, if you look at the history of the field of development economics, a lot of the major sort of step changes in the quality of research have been driven by innovations in measurement. In particular, the standardization of national accounts data in the 1970s changed the way that people evaluated macroeconomic policy. And similarly, the advent of these nationally representative household surveys in the 1980s and 90s and continuing today really changed the way that people approached the microeconomics of development. And so, what I think is happening now is there's a new sort of phase change that's being enabled by novel approaches to measuring welfare and poverty. And so there's a very large literature that I'm not going to talk too much about how we define welfare, whether we think about income or wealth or expenditures or subjective well-being or stress levels or body for weight indices. I'm going to sort of step us back from that and talk at a slightly higher level of generality. But the point is, for all of these traditional ways of measuring welfare are very expensive and very time-consuming. So if you look at the gold standard sort of nationally representative household survey, these take years to conduct and cost tens of millions of dollars. And what happens in one of these surveys, and I'm guessing a lot of people in the room have been involved in this, is you go and you sit down with a household and you spend literally 3 hours or maybe 2 or 3 days going through a very, very long list of hundreds of questions just to get a sense of the welfare of that household. And so this is a very reliable technology for measurement, but it's not something that scales very easily and not something that can be deployed in rural, conflict-affected regions of Afghanistan, for instance. And that's part of why you see these very long time lags between nationally representative household surveys. And so this is just showing you the state of survey technology in Africa, where the average African nation has only had one nationally representative household survey in this 10-year period between 2000 and 2010. And so how does big data, how does machine learning provide a new option for measurement? So for a long time, since the 1970s, people have thought about using night lights data to measure welfare. And so again, since the 1970s, people have noticed that if you look at the images taken by satellites orbiting the Earth at night, you see that the regions of the planet that glow the most, that emit the most night lights, tend to be the wealthiest. So people have used this to look at welfare in developing countries, but there's some problems. So on the left, I'm showing you the United States, and on the right, I'm showing you Nigeria. And what's very noticeable in this graph, so maybe over here there's a lot of variation in nightlights. But when you look in Taruba State in the east, it's just this big black hole. And that doesn't mean that everyone living in this state is in a state of abject poverty, right? These people are not uniformly suffering. It just means that you don't see light being emitted from a satellite in the evening, because what the satellites capture are street lamps and built infrastructure. They don't capture the quality of electrification of individual households and other things that might correlate with welfare. So nightlights are useful, but they're really just one step in this long chain. And so what I'm going to talk about for the next 20 minutes or so is a new approach in the research literature to building poverty maps and measuring welfare using non-traditional data. And I'm going to focus on the two types of data that seem to be most useful in underdeveloped or developing countries. In particular, remote sensing data, so high-resolution daytime satellite imagery. You could also think about using Google Street View data, like the images you get of the facade of a house, sort of falls into this first category. And the second is digital trace data, and in particular, data that's coming from mobile phone networks, because as you know, even in the poorest countries in the world, mobile phones are very common. Now, they're not ubiquitous. In sub-Saharan Africa, maybe the median penetration is like 60%, but that's still a lot of data from a lot of people in places that would be hard to send normal survey methodology. Okay, so the outline for what I'm going to talk about, I've given a little bit of motivation. I'm going to talk about each of these two approaches in turn, and they both rely fundamentally on machine learning. And so since I know this is a fairly heterogeneous audience, I'll spend like one slide saying what machine learning is in like an image, and then I'll talk about how we are using machine learning in this context of measurement. And then hopefully there'll be some time to talk about where the state of the research frontier is, and some of the other applications that have nothing to do with measuring poverty, but that are building off of this. For instance, financial inclusion uses a lot of the same ideas and methods. Okay? And I'm happy to take clarifying questions. If they seem to be taking too long, then maybe we'll cut off questions. But because I know it's a diverse audience, please ask me if there are things that are not clear, or if I'm speaking too fast. Okay, so the one slide crash course on machine learning. So the example I'm going to give, which is everyone's favorite example, I teach a graduate class in machine learning, and this is like the first slide on the first day of class, is say you're a company, say you're a bank, or say you're a phone company, and what you want to do is you want to predict which of your customers is going to leave you for a competitor, and we call this churn, right? It's like the opposite of adoption, when you're going to lose a customer. This is a very relevant question for a lot of companies that care about their customers. So the way this would work with like a traditional statistical procedure or statistical programming approach would be to say that, okay, we have some data on the customers, we'll call this X, and this might define things we observe about the customer, like their age, their gender, where they live, how much money they've been spending on their credit card over the last couple months. So based on that data, we want to make a prediction about whether that person is going to churn or not. And so the way that traditionally this problem has been approached is that, smart people in the bank who have spent a lot of time working with customers will say, I've observed in the past that when customers reduce spending consistently over several months, that's a sign they're going to leave us. Or I've noticed that around January, after the holidays have passed, that's a time when customers are going to leave us. And so they'll write a program down that basically says, based on these data, according to the rules that I have dictated, based on the intuition I've accumulated, I'm going to create a prediction for each customer of whether or not they're going to leave the company. Okay? So that's like the traditional paradigm that drives like 98% of computer programs in the world. This is also how like a video game is written. Now, the way machine learning works is very similar, but with this one critical switch, which is that the idea is, instead of feeding the computer data in a program that's written beforehand, we're going to feed the computer data and the output for people that we've observed behave in the past. So the idea is, we're a bank, we've had thousands of customers, and we've observed over time whether those customers have left us or not, whether they've churned or not. So what we're going to do is we're going to use the computer to discover the relationships from the data that tell us whether or not the person is going to churn. In other words, all of the computational power of the computer is devoted to constructing a program for us. And we can think of that program as just a function that maps the input data, which is the characteristics of the customers, to the output data, which in this case is whether or not that customer left us. Okay, so that's the one slide version of machine learning, and I'm going to show you like how we think about doing this in the context of predicting poverty. So, this is the same figure from the prior slide. We have this machine learning paradigm. We have some input data, some output data, and we want to use this to construct a program or a function. So the idea here, this is the first of the two approaches. So I'm going to talk about the satellite imagery approach first, and then the digital trace phone data approach second. And they're very similar. The idea is the input data to the computer is satellite imagery, right? Data that we get from Google Maps. Now, any one of you, as long as you know how to write a computer program, can go download for free 25,000 high-resolution satellite images from the Google API. Right? So researchers did this. They did this for several days and with many people, so they had millions and millions of high-resolution satellite images. It's the same images you see if you go to the Google maps.google.com and look at the satellite view. Right? So that's the data that they're using as input, and then they have some output labels. In other words, they know for certain satellite images what the correct answer is. In other words, what the actual wealth is of the region covered in the satellite image. And then they just use sort of fancy machine learning models. They don't actually do much to customize these models. They just take things off the shelf and use that to figure out what the program is that can map images to wealth. And then once you've done this, the nice thing is you can take the model that you trained on labeled images and apply it to unlabeled images. So just like in customer churn, we use historical data on customers who've churned or have not, and then we use the model learned there to predict for new customers where we don't know if they're going to churn or not. And so here what we're doing is we're using labels on known images to predict labels on unknown images. And from that, you can get very high-resolution maps. So one more slide on the details, because I think this is like a very clever approach, and it's actually very easy to understand at one level. But the subtlety is really just setting up the problem in a way that is conducive to machine learning. So the key of any machine learning application is to construct a properly labeled data set. And in the case of this, what this means is we want to match spatial data from satellite imagery to labels from surveys. And so the idea here, this is a map of Rwanda. This is a map showing each of 500 villages, the centroid location of the villages in Rwanda. And so the idea is they use existing survey data. So there was a large nationally representative survey that was conducted in Rwanda in 2010. And in that survey, they sent people to each of these 500 villages. And in each of the villages, they interviewed roughly 30 different households, chosen randomly from the village. And in each of those households, they did this. They spent a few hours sitting down with the household, asking them hundreds of questions about the quality of life in the household. And in particular, they asked a bunch of questions that allow them to say something about the wealth of the household. Now, again, measuring wealth is a latent thing that's very difficult, but the way that economists tend to do it is to ask a bunch of questions about observable characteristics that are correlated with wealth. Questions like, does this household have a bicycle? Does this household have a television? How many rooms in the household? What's the roofing material? Is there indoor plumbing? And then you take all of these questions, there might be 20 or 30 questions, and you collapse them into a single index that tells you something about the total or relative wealth of the household. The point is, for each of the 30 households in each of the 500 clusters, we have a wealth index, okay? So then, the trick is to say, the average wealth of each of these villages is going to just be the average wealth of the 30 households that were surveyed in the village. And that's like the magic. So all of a sudden, we have labels for each of the villages in Rwanda of some measure of the ground truth, welfare, or wealth of that village, okay? At that point, the idea is to match the ground truth labels, which come from tried and true gold standard survey methods, to non-traditional data. And there are a lot of details that I'm not going to bore you with, but the basic idea is you take the satellite imagery that covers the village, and this is like what one satellite image looks like, and then you extract characteristics of the image. We call this feature engineering. And we could imagine a lot of different ways to do this, right? Like, if we were to sit around a table and if we had infinite time, we could look at every image and label things in the image that we think might relate to wealth, like how many houses with tin roofs are there in the image? Or how does the quality of the road in that image look like? I mean, intuitively, when you look at satellite imagery, some part of you can say, oh, this image is from a place that's relatively wealthy, and this is from a place that's relatively poor. And the trick is to encode that intuition into features. Now, even Rwanda, which is a very small country, there's millions and millions of images that cover Rwanda. So it's not practical to have humans go through each image and encode these features by hand. So there's a little bit of black magic where they use these deep learning algorithms, these deep neural networks, and I'm happy to talk about this in more detail, but I don't think the details are interesting. You can, for the purposes of this, all you need to think is that these fancy algorithms that were developed by Google to label images on Google image search, you can apply to any image and use that to turn that image, which is this very high-dimensional, difficult data structure, into a nice set of features, metrics. Now, these metrics don't capture the things I was talking about earlier. They just capture latent properties of the image, like how bright is the image, or even things that we couldn't describe that are very difficult to interpret. But let's assume that they've done this, and then for each of the villages, you not only have a wealth label, but you now have an input vector, x, that tells us the characteristics of the images in that village. So now we're in predicting customer churn land. All we need to do is apply whatever supervised machine learning algorithm we want that basically learns the mapping from x to y. And once you've done that, then you can apply that function to an arbitrary satellite image. So we can take, the image here, pass it through this function here, and it will give us a prediction of the wealth of the people living in that very small area. And that's how you get to these very granular maps of predicted wealth. So that's the first approach. It has a lot of advantages. In particular, satellite data is globally available, and the technology used to capture satellite imagery is increasing extremely rapidly. So there's a company in San Francisco called Planet Labs that takes a photo from takes satellite imagery of every square foot of the Earth's surface every day. Right? So every day you can get an updated image of any place on the planet. It's 5 years ago this was not the case. So the technology is improving rapidly. This increases the potential for very impactful applications, which I'll come back to later. But there are also limitations with this approach. So a lot of the things that we care about measuring are not necessarily visible from an overhead satellite, right? Yes, wealth is maybe visible, and yes, maybe quality of agricultural land can be measured from a satellite. But if we want to know about is someone in the household sick right now? Or did the people in that household leave because of the recent drought? You just don't see that very well in satellite imagery, no matter how high resolution it is. And then I have some work that shows basically this, that if you try and predict other measures of welfare from satellite imagery, things like educational levels or educational enrollment levels or height for weight indices, so anthropomorphic measures of well-being, that satellite imagery doesn't work as well. So, some of these things motivate thinking about other approaches to measuring wealth and welfare. So that was this first approach, and what I just talked about, there's this journal article in Science that you can go look up that basically talks about that method in much more detail. Now I'm going to switch to the second approach, which was another Science article that talks about much more details than what I'm going to say now, but that uses phone data to do almost the exact same thing. Okay. So phone data, the basic idea, and again, the trick to all of these studies is framing the analysis and collecting the data such that you can link input data to output data in a methodical way. So the idea here is what we're going to do is we're going to take digital trace data. So in this case, this is data that's collected by the mobile phone operator, and we're going to link it to surveys with mobile phone subscribers, and then use machine learning to figure out the functional mapping from the input data to the output data. So in a little bit more detail, the phone data coming from the phone company, and if you were at ETAM yesterday, you saw me talk about a different data set, and the same approach, it's the metadata of the phone calls. So this is like, it's not the content of the text message I sent to Raymond this morning, it's the fact that at a particular point in time, a particular phone number communicated with another phone number, and then very importantly, something about the location of the two phones at the time of the phone call or the text message. And this is another map of Rwanda showing you the location of all of the cell phone towers in the country. And so what the phone data allows you to do is to locate a given person within the rough catchment area of a cell phone tower at the time when they make a phone call or receive a phone call. Okay? And so this is showing you when you have billions of data points that look like this. This is actually Afghanistan, not Rwanda, but how one day of phone traffic on the network looks like. And you can see that what we know about the economic linkages between Kabul and Herat and Mazar-e Sharif are very visible in the phone records too. Okay, so what we did is we started with a very large data set that looked like this. So it just had billions and billions of log entries that just told us when all of the phone calls happened and between whom they occurred. And then we pulled a random sample of phone numbers from this data set and called them. So I did this when I was a PhD student, sat in Kigali with a team of undergraduate students, made phone calls to these anonymous phone numbers, and then asked them questions, the same questions that are asked in the household surveys about, does your household have electricity? What is the roof of your household made of? Do you have a television? And so forth. So the same way we used the survey data, so we called in total roughly 850 different people, and for each of those 850 different people, we can construct a wealth index that tells us about roughly how wealthy they are. And for each of those 856 people, we have all of their transaction data. Okay? So there's one critical step missing before we can just throw machine learning at the problem, which is we have to have a way we call it feature engineering again. So is to extract from these transaction logs, which are just, again, billions and billions of very boring little rows in a database, we want to convert that into something that tells us about the characteristics of the phone user. So with the satellite data, we use these deep learning algorithms. Here we use a different approach, but the idea is we want to get from the raw data to measurements of phone use that we think are predictive of wealth. So I invite you all to think about that for a second. Like, if I gave you everyone in this room's phone records, and there's some people in this room who are very wealthy, and some people in this room who are not as wealthy. I'm sure there's some students in the room who are not as wealthy. But we had records of the phone transactions that those people would make. Like, think about what aspects of phone use you might use to predict whether the person is wealthy or poor. I don't know what the answer is in Mexico, but in Rwanda, where we did this study, basic things like the number of calls a person makes per day are highly correlated with the wealth of the person because it costs money to make phone calls. But there's also much more complex characteristics, like the number of international calls a person makes. Or there's this interesting property, the way the phone network is structured in Rwanda is only the caller pays for a call. It's all prepaid phone use. So if you look at the ratio of outgoing calls to incoming calls, it turns out that the wealthy people are the ones who initiate a lot of calls, and the poorer people are the ones who receive a lot of calls. And there's this whole dynamic of beeping and flashing and missed calls where, Raymond is a senior professor, he's very wealthy, I'm a junior professor, I'm very poor, and I want to talk to him, so I'll call him and hang up. And then he knows, he's the wealthy guy in the relationship, so he's supposed to call me back. And this is very, very common, not just in Rwanda, but in a lot of countries. And so, lo and behold, if you look at that, the flashes or these missed calls that people send, that's indicative of relative poverty. So we're not going to actually say, remember, we don't want to be the phone company that relies on the intuition of the analyst to say which, it's the missed calls that tell us about wealth and poverty. We're going to use machine learning to do this. So we have our X's, which are number of missed calls, number of international calls, number of structure of a social network, all of this beautiful information we observe in phone data, like the mobility patterns of individuals over space. So we have lots and lots of features, and then for 856 people, we know how wealthy they are because we talk to them on the phone. So then what we do is we just connect the dots and use machine learning to figure out amongst the 856 people that we spoke to, there's some who are wealthy and some who are poor. What are the best predictors of poverty in this data set? And then we throw all that into a machine learning model that allows us to do something. And maybe I'll skip this slide in the interest of time. So when we do this, it turns out that we can predict with a reasonable degree of accuracy how wealthy someone is and how poor someone is. So just to interpret this figure, remember I said we have 856 people that we spoke to on the phone for whom we know how wealthy they are. And so on the y-axis, I'm plotting the actual wealth index, which ranges from -3 to +3. So there's 856 points here. The y value tells us how wealthy they are, according to what they said in the survey. And then the x-axis is the prediction based on the algorithm. And so, it's not a perfect fit. There's a lot of noise. We thought this guy was really wealthy, and he turned out to be not so wealthy. And we thought this guy was relatively poor, and he turned out to be quite wealthy. But there's a pretty strong correlation. And, the quantitative measurements of the fit of the model are over there. But this is just the first step. We don't actually really care about this. What we care about is using the model that we built here to predict for other people. So in particular, at the time of this study, there were about 2 million mobile phone users in Rwanda. And because as they use their phone, they're generating GPS or geographic identifiers that allow us to say something about where they live, what this map is showing is the approximate distribution of mobile phone owners in Rwanda. Right? So we have this very, very granular, this map has 1.5 million little cells. Each cell corresponds to roughly one mobile phone subscriber, where we think their home location is, based on where they've made their phone calls from. Now, for each of these cells, we have the phone use data, but we don't know how wealthy the person is, because we can't afford to survey 1.5 million people. We only surveyed 856 people, but we have this model that we constructed on those 856 people that allows us to predict the wealth of this person. So in particular, we can fill in each of these cells the predicted wealth. And from this, we can again generate these very, very high-resolution maps of the predicted distribution of wealth and poverty. And if you remember the map I showed you before of Nigeria, that was basically uniformly black over here, this shows you that you get a lot more variation when you're using mobile phone data. Okay, so that's sort of like the core methods I wanted to go over. I think it's worth stepping back a second and asking these higher order questions. So first of all, actually one more slide on the methods is, I've generated these very pretty maps that are conducive to publishing academic papers, but there's a more important question, which is, are they actually accurate? And there's a chicken and the egg problem here in that we don't know if they're accurate because the problem is we don't have, the only way to generate a map that looks like this is to use very high resolution data. Like national survey institutes, I wonder if INEGI has anything that would tell us the distribution of wealth in Mexico at this level of granularity. If they do, I bet they wouldn't make it publicly available to anyone. What they have in Rwanda, so if the lowest level of geographic disaggregation at which nationally representative data is available in Rwanda is at the district level. So, this is the state of the art using traditional data from Rwanda, and when we aggregate the maps that look like this, these cells up to the district level, this is what our predicted distribution of wealth is just based on the phone data. And so what you can see is these maps are relatively similar. Now, there are differences, it's not perfect, but the correlation is quite high. Okay, so the existential question that all academic researchers face, so this is like a nice proof of concept, but could these actually be used in practice? And so I'll go back to that first slide and say that I should say that at no point am I implying that one should use these methods to replace traditional survey methodologies. Like, absolutely not. But if you're in Afghanistan and you can't afford the $25 million nationally representative household survey, this is like a Band-Aid, right? This is like a stopgap way to get a rough approximation of the distribution of wealth for very low cost. And so remember I said that our map is correlated with the ground truth, the correlation is 0.9. If you look at the nationally representative household survey that was done prior to this one, so this one is done in 2010. Prior to 2010, the most recent survey was in 2005. And if we built a map of the wealth of Rwanda in 2005 and compare that to the wealth of Rwanda in 2010, the correlation is exactly 0.92 also. So I think the takeaway here is that this method can produce district-level estimates that are about as accurate as a 5-year-old nationally representative survey, but much, much cheaper. And I think for researchers in the room, this is exciting because it provides a low-cost option for getting maps like this that you can use as inputs to other social science research questions. All right, stepping back one step further, let me sort of talk about where I think the state of this literature is, where the state of research is. So what I've presented today are two different approaches to static prediction. In other words, at a single point in time, can we estimate the distribution of wealth with high spatial granularity? And I think the answer is yes, right? There's many, many papers, some that I've been involved in, most of which I haven't been involved in, that demonstrate this. And one of the key applications, I think, for policymakers is to think about resource allocation and poverty targeting, right? In other words, you want to allocate resources to the people who have the highest marginal utility of consumption. These maps can help tell you that. What we can't do, and where I think like really the holy grail is over the next few years in this research literature, is dynamic prediction. In other words, not generating a static map of the distribution of wealth at one point in time, but actually inferring changes in welfare at the household level over time. Because, as I said, satellite images are updated every day. Phone records are updated every millisecond. If we could take those maps and generate them every month, then this unlocks really key applications like impact evaluation, right? One of the big constraints to doing policy impact evaluation is typically you want like a before policy snapshot of the distribution of welfare and an after policy snapshot of the distribution of welfare. But collecting those snapshots is very expensive. This is a very low-cost way to potentially generate those snapshots. The other application that I think is very promising is disaster response. So I'll show you one more video. This is the same phone data from Rwanda, but now I'm showing a different version of it, which is a single day. So February 3rd, 2008, this is the time of day. So each frame in this video is 1 minute. So this is a minute in the life of the mobile phone network. The cells in the network are shown as red if there's a lot of outgoing calls from that district, and blue if there's not a lot. And so what happened is, as I was talking, there was an earthquake at 9:30 in the morning on February 3rd, 2008, and you can see all of the call traffic suddenly concentrates in the region near the epicenter. And so imagine if you could combine the dynamic variation in the phone data, use that to generate estimates of who is actually most impacted by the earthquake, then you could think about all sorts of novel approaches to doing disaster response. So I've talked a lot about basic measurement, and if you'll give me 2 more minutes, I'll just sort of jump to something totally different, but hopefully you'll see the connection, how this is still machine learning applied to development. And I'll talk for a minute about financial inclusion. So what I've told you in like the second third of the talk was that I can use mobile phone data to predict how wealthy you are or how poor you are. Well, banks have figured out that they can use mobile phone data to predict whether you're going to repay a loan. And so what they're doing all over sub-Saharan Africa is using mobile phone data to build credit scores, using machine learning, and then using those credit scores to give loans to people who are totally outside of the normal formal financial ecosystem, because they live nowhere near a bank, they have no collateral to speak of, and they have no data that the like National Institute of Statistics would have access to that would allow the bank to construct a credit score. So this is really exciting. In Kenya, this statistic is staggering. 20% of the adult population currently has an outstanding loan to the phone company or one of these companies. Both Tala and Branch operate in Mexico, so you guys could all sign up. I'm not paid by them. You probably shouldn't do this, but you could download the Tala app or the Branch app and give it access to the data on your phone, and it would give you a credit score, and then you might be able to get a loan. This is a huge funding sensation in Silicon Valley, but I think there's a narrative in development literature that this could be transformative, right? We're providing access to credit to billions of unbanked. This is something that development economists tend to get excited about, but there's all sorts of reasons to be concerned. Now, is providing $5 consumption loans to ultra-poor people really going to help lift them out of poverty? Maybe, but we don't know. But what we do know is that the banks don't care. The banks just want people to repay their loans, and so that's how they're making the lending decision. What about the fact that when people know that their phone is being used to make a loan decision, that they're going to start to use their phone in a way that gets them a loan? And so if you Google online, how do I increase my Branch credit score, there's thousands of results of people who are speculating on, well, you need to add more Facebook friends, or you need to have a larger mobile money balance. And so, this is a big problem that these companies haven't really dealt with. And then these huge, bigger questions, and this affects, of course, not just the financial inclusion application, but everything I've been talking about. What are the privacy and ethical implications of monitoring non-traditional data sources to infer characteristics of populations that have historically been off the national statistical radar? And particularly in fragile and conflict-affected regions or authoritarian regimes, this could be a major concern. All right, so just to summarize, I think there's three takeaways. One is that there are really high-impact, potentially transformative applications of big data and machine learning to really core questions in development. The second is that even though there's a lot of potential, there's very, very little evidence of actually having that transformative impact that people think it might have. So there's lots and lots of papers that show how you could do something really transformative, but very few documented examples of someone actually doing something transformative. And then the last thing I'll point out, and this was on the last slide, is that in order to sort of connect these two dots, there's a lot of important challenges that need to be solved. Some are technical, like machine learning, innovation, and deep learning, and so forth. But some of the biggest ones are about data sharing. How do you unlock the data so that researchers can innovate these methods? How do you do it in a way that preserves the privacy of the people whose data is being shared? And so on and so forth. And so this will be the last thing up here. This is, I think, a nice motivating slide, a quote from an opinion piece by Sendel Mulanathan. So he was writing, and he writes, why should the financial services industry, but I'm going to substitute internet industry, because I think the backstory here is that all of the innovation in methods is coming from Silicon Valley. These are methods that are designed to sell products to people to predict churn, and we're just taking them and applying them in a slightly different context. I think that's why there's a lot of potential. And so he asked the question, well, why should these industries, where it's just for money, be it so state-of-the-art when the aid industry is using, relatively antiquated methods and technology? So I'll leave it off there and hand over the mic to Raimundo. Thank you.
Okay, las preguntas están por ahí pasando para que se las puedan pasar. Tenemos unos minutos para hacer varias preguntas, pero bueno, mientras recibo varias de sus preguntas, I would like to ask you, Josh, if you are currently working on this topic that you mentioned on dynamic measurement, welfare. I think is very important. I mean, and if you have the phone data and other type of data that you can answer maybe some types of questions, maybe not causal questions, but even correlations with this type of data. I think they are very important. So I don't know if you're currently working on that.
Yeah, no, I think, as I said, I think that is like the holy grail right now in this line of research, is being able to use non-traditional data to measure accurately changes in household welfare over time. So I'm working on that, yes, with satellite data, with phone data, and with Facebook data. And the short answer is it's very hard. And I had a slide, and let me just sort of pull it up here in case people are interested. You can think about why this might be hard to do. And these are some of the issues, right? Like, it may be that your welfare changes, but you don't actually, your input data doesn't change, like the satellite image example I gave earlier, right? Like, a child in your household might get sick, and you might have to stay home from work, and this might negatively affect your welfare, but a satellite image isn't going to pick that up. Or if we're using phone data, now maybe if that situation happens, your phone, the pattern of phone use will change, but maybe not. Maybe people don't change how they use their phone in response to these events. And I think another fundamentally challenging issue is that the models you fit are fundamentally designed to generalize at one point in time. So think about phone use, right? Like I told you about how in Rwanda, sending missed calls is a sign of relative poverty. What if the phone company decided to change the structure of the phone billing so that both the caller and the receiver paid for calls? Well, then this missed call phenomenon would no longer be predictive. So these models don't necessarily remain accurate over time because the underlying dynamics in the population can change in a way that destabilizes these models. So the short answer to your question is we and a lot of groups are working on it, but the results I've seen, both from my group and other groups, is creates reason for being measured in your optimism. I think it's not going to be like a quick thing that people come up with.
So let me ask you some 2-3 questions, then you can answer them. So lots of questions, thank you. So how, maybe if you can elaborate a little bit more on the representativeness of the results. And then, I mean, you mentioned this on the chicken and egg problem, but can you elaborate a little bit more on, especially when we want to know wealth at, for different regions? And also I have a couple of questions on whether you can extrapolate these results to other countries. Even though you use the data for Afghanistan, maybe you can extrapolate the results to other countries. And what is your experience doing that?
Yeah, those are both very good questions. So the first question was about representativeness. And just to put a very fine point on the question, in the case of Rwanda, at the time we did the study, only 15% of the Rwandan population used a phone or owned a phone. So while our method is very good at telling us or predicting the relative wealth of a phone owner, given that they're using a phone, there's 85% of the population for whom we cannot make a prediction. So, you know, fundamentally, if what we care about is knowing the wealth of a person, this method is useless. For instance, if you're making lending decisions based on phone data, you can't lend to people that don't have phones. So I think there is a fundamental limitation there. And we know that the people who own phones or the people who generate digital traces more broadly are non-representative. They're wealthier, they're men, they're better educated, they live in urban areas, so forth. But what we do know is that, or what we observed in Rwanda, is that even though we only observed 15% of the population, as I showed you, the map at the district level of the distribution of wealth accurately reflected the total distribution of wealth of the entire population. And so we can talk about why that might or might not occur, but I think there's still hope that you could use data from, you know, people in a region, from the device users in a region, to draw inferences about the non-device users in the same region. So let me just also briefly talk about the second question you asked, which is about generalizing from one region to another. I think the short answer to your question is no. So I've actually tried that exact thing. I've tried to use the model I trained in Rwanda to predict wealth and apply it in Afghanistan, and it doesn't work at all. And I think the reason is the same reason that we have difficulty generalizing from one point in time to another, is that the fundamental social dynamics that relate wealth and phone use in region A are different than in region B, right? Like is it the case in Mexico that the caller pays for the call, or does the recipient also have to pay for the call? Just the call? Okay, so maybe that's a bad example. In the US, the recipient gets billed the same as the caller. And so there's no reason to think that that Rwanda model would work in the United States. So I think there is a fundamental generalizability problem. And at the end of the day, what this means is that this is an external validity issue, that you have to make sure that the data you're training your model on is representative of the settings in which you want the model to be applied to. So don't train an Afghanistan model in Rwanda, train it in Afghanistan.
Other questions. So we have a question on how do you feel about the theory? I mean, you talked about the, you inverted the decision on the outcome and the data to get a prediction, but then what is the role of theory with this prediction? And then I have two other questions, basically, or I have 3 questions on how to get this data. How did you do it? And how do you think in Mexico someone can get this type of data? And then, well, maybe the third question is, I mean, you talked about poverty. What about the other end of the distribution? Can we use this model to predict how wealthy individuals are and how to measure inequality with this type of data?
Yeah, these are all very good questions. So the role of theory, I think just being perfectly honest, most of what I focused on today was about measurement and about prediction. And all I cared about was having accurate predictions. So in a sense, it's a very atheoretical exercise. Now, I don't think that means that there's no role for theory in these methods, or that there's no role for these methods in testing theory. Like, I just think that what I was talking about today is like one small input into that exercise. For instance, there's all sorts of really fundamental theoretical questions about development that involve, how different interventions affect livelihoods. And all I'm saying is that if we have accurate measures of livelihoods, that will make it easier to answer those theory questions. Now, there's a much larger debate about whether machine learning can test causal hypotheses and so forth, and I think let's abstract from that. But I think at a very superficial level, for this sort of method, I share the desire and the instinct that there should be theory, but I think this is a case where actually all we care about is accurate predictions. I don't really care if those accurate predictions are based on some fundamentally sound economic theory, as long as they're accurate. The second question was about getting the data. And I think there are people in the room who might have better insights on who to talk to. Some of them are sitting in this audience about getting specific data in Mexico. I think more generally, for very good reasons, banks and phone companies are very careful about who they share their data with and how. I think the good news is that there are better and better methods and technologies for sharing data in a way that preserves the privacy of the individuals who are generating the data, coming from the security and privacy community in machine learning, in computer science. I think the countervailing force is, there are the Facebooks of the world and all of these scandals of inappropriate sharing of data in a way that just creates a lot of paranoia and the sense of risk from private companies. So I don't think there's a simple answer to the question. I think in general, you have to establish a relationship with the person who controls the data, make sure they trust you, and make sure that the proper protections are in place, that their interests are protected. But aside from that, it's hard to say. The third question was about, I was talking about predicting poverty. Could we use this to predict wealth or inequality? I think yes, right? Like the maps I showed you were actually maps of wealth. I just say they're maps of poverty because I care more about poverty. But this actually ties back to your first question, or someone's first question, or the second question about sharing data. The way we got the data from the phone company in Rwanda in the first place is that they were interested in having maps of wealth so that they could know where to advertise, right? And so
what I wanted was a map of poverty so that I could tell the government, where the areas of extreme need were. But those are fundamentally the same thing, right? Wealth to the negative, 1 over wealth is poverty. And so I think absolutely yes. And exactly as I talked about earlier, what the banks are doing is they're predicting repayment, right? Which is very similar to wealth. But the methods, you could use it to predict gender. You could use it to predict, and this goes back to what are the ethical uses of these data. You could use it to predict ethnicity. You can use it to predict political affiliation. There's a study that was in the proceedings of the National Academy of Sciences last year where researchers used Google Street View data, so the images of the fronts of houses, to predict political affiliation of neighborhoods. So there's the methods are application agnostic. It's really just, can you get the labeled data set up in a way that you can apply the methods? And the answer is, in general, yes, for better or for worse.
And to close, Josh, what is your view of the field in 5-10 years with all these data and new methods? What do you think is going to happen?
Yeah, I don't know. I mean, I think we will make progress on this dynamic prediction problem, and I think that will really open up the door to widespread use in the research and policy community. I think more generally, it's a really exciting time for people, myself, students, others, to work in this space, because it's only over the last few years that we've had massive scale satellite data and massive scale digital trace data coming from developing countries. And also, at the same time, over the last 5 to 10 years, the computing technology has evolved to a state where it's actually very cheap to analyze petabytes of satellite data. And you can, not just have the computing power, but there's open source toolkits that make it possible for anyone to do it. So I teach at UC Berkeley a master's class on big data for development, and the first problem set has them replicate all of the results in that first science paper. And, these are smart students, but they're not like Stephen Hawking's of the world. It takes them 3 weeks to download all the data themselves, take an open source machine learning toolkit, and combine the two, and they have the results. So the technology is widely available. It's pretty intuitive for people to use, and the data is there. And so I think we're just really at the cusp of what the really exciting applications might be.
Thank you. Acabamos perfecto en tiempo. Vamos a tener 15 minutos de receso y regresamos para la siguiente mesa redonda. Tenemos café y galletas. Muchas gracias, Josh.
Gracias.